From where did all this come from? In every direction we care to observe, we find stars, galaxies, clouds of gas and dust, tenuous plasmas, and radiation spanning the gamut of wavelengths from infrared to visible light to gamma rays. The universe is always and everywhere filled with matter and energy, no matter where we look or how we experience it. Yet, it's only natural to assume that it all came from somewhere. If you want to know the answer to the biggest question of all, the question of our cosmic origins, you have to pose the question to the universe itself and listen to what it tells you. Welcome to actual space. Today, we embark on an extraordinary journey, a journey to the beginning of the universe. How was our universe created? How did it become the seemingly infinite space that we are aware of today? And what will happen when our universe ends? Scientists have been puzzled by these problems since the beginning of time, and their answers have produced some very strange and interesting theories. Since the Big Bang explosion either marked the beginning or the end of the universe, we are still working to understand it completely. The subject of how the universe originated and how our world came to be has been asked by many generations and civilizations. The insatiable curiosity about its origins remains as strong as it did thousands of years ago. Many civilizations, including the Maya, Chinese, Inca, Arabs, Greeks, and Egyptians, held the belief that a superior power was the creator of everything. Their theories and views about how the world is shaped differed. They believed that heaven, hell, and earth were in the middle. Then came the geocentric model. The Greeks theorized that the earth was slightly spherical rather than flat. There were stars in the sky, and several celestial bodies were in orbit around the planet. Subsequently, the heliocentric model emerged, explaining that the earth rotates around the sun, which is at the center of the universe. According to this notion, stars are fixed at a distance. Many years later, around 2,000 years ago, Copernicus set his heliocentric theory, which was approved after his death. The universe consists of everything you can think of: nature, oceans, the world, and even our solar system. According to a study on universe evolution theories, the Big Bang theory is the most widely accepted theory. Nothing comes from nothing. For something to exist, there must be material or a component available. What happened in the initial instance to create the materials that caused the Big Bang, and where did that material come from? It is still unknown how our universe came into being or whether there was something that existed before. But physicists are still working to find the answer. We would need to explain the initial quantum state of the entire universe in order to provide a meaningful response to the question of how something could exist out of nothing. Any attempt to achieve this is still highly speculative. Some of them appeal to supernatural forces, like a designer. Nonetheless, there are still alternative plausible answers that fall within the domain of physics. These include the multiverse, which is made up of an endless number of parallel universes, and cyclical models of the universe that undergo repeated births. Roger Penrose, the 2020 Nobel Prize-winning physicist, put up a tempting but contentious conformal cyclic cosmology concept for a cyclical cosmos. Penrose was inspired by an interesting mathematical connection between a very hot, dense, small state of the universe, as it was at the Big Bang, and an extremely cold, empty, expanded state of the universe, as it will be in the far future. His radical theory to explain this correspondence is that those states become mathematically identical when taken to their limits. As unbelievable as it seems, all of the matter in our universe may have originated from a complete absence of matter. From this perspective, the Big Bang comes from almost nothing. Nevertheless, the universe did start 13.8 billion years ago, and this video is all about what happened after the Big Bang. The Planck era, despite what its name may suggest, the Big Bang was not an explosion in space. Rather, it was the appearance of space everywhere in the universe. Everything in the universe was compressed into an incredibly tiny singularity, a point of infinite heat and density, some 13.8 billion years ago. That speck was the source of everything in the universe as it exists today, including all protons, atoms, and other matter. This was the first known epoch of the universe, also referred to as the Planck epoch or Planck era, a time so early in the history of the universe that it defies our best understanding of physics. This era took place just 1/10,000,000th of a trillionth of a second after the Big Bang. At this point, quantum fluctuations started to affect both space and time. Usually, physicists deal independently with general relativity, which operates on vast cosmic scales, and quantum mechanics, which governs the micro-world of particles. But to truly understand the Planck epoch, we need a complete theory of quantum gravity that merges the two. Though there have been attempts, such as with loop quantum gravity and string theory, we still do not have a perfect theory of quantum gravity. Ordinary space and time are usually viewed in these attempts as emergent, like the waves on the deep ocean surface. Because we are beings rooted in the macroscopic universe, space and time seem senseless. But what we experience as space and time are the result of quantum processes functioning at a deeper microscopic level. We can no longer rely on our ordinary understanding of cause and effect, since in the Planck era, our standard concept of space and time breaks down. Despite this, all candidate theories of quantum gravity described something physical that was going on in the Planck epoch, some quantum precursor of ordinary space and time. But where did that come from? Physicist Max Planck created a system of units in the late 1890s to make the expression of physics rules simpler. We could calculate these identical Planck units using just 5 natural constants, such as the gravitational constant and the speed of light. We could even calculate them using aliens from Alpha Centauri. The Planck units consist of length, mass, temperature, charge, and time. For a moment, let's think about the Planck length unit. The proton is about 100 million trillion times larger than the Planck length. To put this into perspective, if we scaled the proton up to the size of the observable universe, the Planck length would be a mere trip from Tokyo to Chicago. The 14-hour flight may seem long to you, but to the universe, it would go completely unnoticed. It was surprising to discover that the limits of the Planck scale, which was initially developed as a system of universal units, also happened to be the limits at which the currently accepted laws of physics operated. During the Planck era, the universe was so small that our laws of physics break down. To dive deeper back in time, we'll need new scientific language. Although we are unable to observe what truly occurs at the Planck scale, scientists can speculate. At this energy, the 4 fundamental forces, gravity, electromagnetism, the weak force, and the strong force, finally combine to form one superforce. Superstrings and quantum gravity are some possible phenomena that could be dominant at the Planck energy scale. We need new, unbreakable physics to understand anything beyond the Planck scale. The period of time immediately following the Big Bang, known as the Planck era, began at time 0 of the Big Bang itself and ended 10 to the power of -43 seconds later, which is 1 Planck second. We are unable to use current technology to measure the length of this moment since it is so small. These figures are beyond our ability to fully comprehend. There was no such thing as original matter because the universe was created in an extremely hot condition, so hot that everything was pure energy. The universe was about 100 million trillion degrees, or 10 to the power of 34 Kelvin, in temperature and roughly 100 million trillion times smaller than a proton at the beginning of the Planck period. Just to give you an idea, this is the size of an atom. The typical radius of an atom is around 0.1 nanometers, where 1 nanometer is 1 billionth of a meter. Atoms are extremely light and small. They are made up of subatomic particles, protons, neutrons, and electrons, which are even smaller and lighter than an atom. The Big Bang created the universe, which has been expanding ever since. However, time and space do not exist in the universe until it reaches the Planck scale. Space gets compactified, but time stays undefined. According to string theory, there were 10 dimensions in the universe during the Planck epoch, but those dimensions collapsed to 4. One way to visualize the extra 6 dimensions would be as extremely tiny hyperspheres between the spaces between basic particles, for enormous dimensions and 6 microscopic ones. The best way to describe the universe during the Planck era is as a 10-dimensional quantum foam that contains continuously formed and destroyed black holes the size of Planck, with no apparent cause or effect. However, the Planck period's vast unpredictability ends after just 100 million trillion trillionths of a second, when the universe gradually cools and grows, signaling the beginning of a new era. For a while, the universe won't appear or act like it does now, but going forward, our existing theories do at least have a chance of explaining what is happening. The grand unification era gravity, the weak force, electromagnetism, and the strong force are the 4 fundamental forces that affect everything we do on a daily basis, from playing basketball to sending a rocket into space to just putting a magnet on your refrigerator. All that occurs in the cosmos is controlled by these forces. All known interactions in science, ranging from the minuscule to the enormous, as well as those we encounter on a daily basis, are caused by these forces. These forces explain how galaxies move, how chemicals react in our labs, how atomic nuclei are structured, and why radioactive decay occurs. They explain the real meaning of commonplace concepts like friction and normal force. Gravity, you surely know of, as it has certainly helped you to fall down before. Gravity is the attraction between 2 objects that have mass or energy, whether this is seen in dropping a rock from a bridge, a planet orbiting a star, or the moon causing ocean tides. Of the fundamental forces, gravity is arguably the most recognizable and intuitive, yet it has also proven to be one of the hardest to explain. The concept of gravity was first put out by Isaac Newton, who claimed to have been motivated by an apple that fell from a tree. He defined gravity as the actual attraction of 2 objects coming together. Many centuries later, Albert Einstein proposed that gravity is neither an attraction nor a force through his general relativity theory. Rather, it's the result of spacetime bending. Objects behave the way a massive ball deforms a sheet of material in the middle and causes smaller items to fall toward the center, similar to how a large object behaves in spacetime. Gravity holds planets, stars, solar systems, and even galaxies together. However, it turns out to be the weakest of the fundamental forces, especially at the molecular and atomic scales. Consider this: how difficult is it to raise a ball off the ground, to raise your foot, or to make a leap? All of those actions are counteracting the gravity of the entire Earth. Furthermore, gravity has very little effect in comparison to the other fundamental forces at the molecular and atomic levels. The weak force, while the other forces hold things together, plays a greater role in things falling apart or decaying, though it is only effective over extremely short distances. The weak force, also known as the weak interaction, is stronger than gravity. It is a subatomic particle interaction that is essential to the creation of elements and the energy source for stars. Much of the natural radiation that exists in the universe is also caused by it. Although its name implies that it is a weak force, it is approximately 10 to the power of 25 times stronger than the gravitational force within the nucleus. Because of its relative weakness in comparison to the strong force or the strong nuclear force, it is known as the weak force. The weak force plays an important role within the nucleus and is responsible for the beta- decay within the nucleus. The nuclear fusion reactions that power the sun and provide the energy required for the majority of living forms on Earth depend on the weak force. That's also why archaeologists can use carbon-14 to date ancient bone, wood, and other formerly living artifacts. Nitrogen-14, which holds 7 protons and 7 neutrons, is created when one of the 8 neutrons in carbon-14 decays into a proton. Because of the predictable rate of decay, scientists are able to determine the age of these artifacts. The electromagnetic force between charged particles, such as negatively charged electrons and positively charged protons, is also known as the Lorentz force. Similar charges repel one another, but opposite charges attract one another. The force increases with the magnitude of the charge, and much like gravity, this force can be felt from an infinite distance, although the force would be very, very small at that distance. The electromagnetic force, as its name suggests, is made up of two parts, the magnetic and electric forces. Scientists initially distinguished between these two forces but eventually discovered that they are actually parts of the same force. Whether the charged particles are fixed or moving, the electric component acts between them to create a field that allows the charges to interact. However, as soon as those charged particles set into motion, the magnetic force, the second component, comes into play. The particles create a magnetic field around them as they move. So when electrons zoom through a wire to charge your computer or phone or turn on your TV, for example, the wire becomes magnetic. Through the exchange of massless force-carrying bosons known as photons, also the particle components of light, electromagnetic forces are transferred between charged particles. But another kind of photon is the force-carrying kind that switches between charged particles. Though technically the same particles as the real and detectable form, they are virtual and undetectable. Some of the most frequently observed phenomena, including elasticity, friction, normal force, and the force binding objects together in a specific shape, are caused by the electromagnetic force. It also produces the drag that airplanes, birds, and even Superman feel when they fly. These actions can occur because of charged or neutralized particles interacting with one another. For example, the normal force that keeps a book on top of a table instead of gravity pulling the book through to the ground is a consequence of electrons in the table's atoms repelling electrons in the book's atoms. The strong nuclear force, of the four fundamental forces of nature, is the strongest one. Commonly known as the strong nuclear interaction, it has a force that is 6,000 trillion times stronger than gravity, that's 39 zeros after 6. The reason for that is that it creates bonds between the building blocks of matter to create larger particles. Protons and neutrons are made up of quarks, and part of the strong force also holds the protons and neutrons in the nucleus of an atom together. The strong force only acts when subatomic particles are incredibly close to one another, much like the weak force. They must be approximately within the diameter of a proton. Once within range, massless charged bosons called gluons transmit the strong force between quarks and keep them glued together. A tiny fraction of the strong force, called the residual strong force, acts between protons and neutrons. Because protons in the nucleus have similar charges, they repel one another. However, the residual strong force can overcome this repulsion, keeping the particles linked within the nucleus of an atom. Grand unified theory is a theory that physicists have successfully created to combine the electromagnetic, weak, and strong forces. The strong force broke away from the others at the time of the grand unification period, which began approximately 10 to the power of -38 seconds after the Big Bang. This separation released a tremendous amount of energy, which is thought to have caused the universe to expand very quickly. The universe expanded by a factor of 10 to the power of 35 in 10 to the power of -32 seconds during the brief period of time known as inflation, from being impossibly tiny, smaller than a subatomic particle, to around the size of a grapefruit in the blink of an eye. Keep in mind that inflationary theory addresses only the observable universe, it says nothing about the whole universe. Postulating this burst of exponential growth helps remove two major problems in cosmology, the horizon problem and the flatness problem. In the universe, what you see is basically the same no matter which way you look. To a very high degree of precision, the temperatures of the cosmic microwave background radiation are nearly identical in all directions throughout the universe. If you really think about it more carefully, this really shouldn't be the case. In reality, you are looking back in time if you simply look in one direction in space, since light moves at the speed of light. The light that reaches your eye or telescope was released years ago. This indicates that there is a limit extending in all directions of about 14 billion light-years. The boundary is actually farther because space itself is expanding, but you can ignore that for the purposes of this example. There is no possibility that anything farther distant could have ever gotten in touch with us. So, you look out with your powerful telescope and can see the cosmic microwave background radiation from 14 billion light-years away. Call this point A. Now, if you look in the opposite direction, 14 billion light-years away, let's call this point B, you observe exactly the same kind of cosmic microwave background radiation. Normally, this would suggest that all of the CMBR in the universe has somehow spread across the cosmos, similar to heating up an oven. Somehow, the thermal information is communicated between points A and B. However, given that points A and B are 28 billion light-years apart, and that no signal can travel faster than the speed of light, there is no possibility that they could have ever communicated in the entire age of the universe. If there is no way for heat to transfer between them, how did they get to the same temperature? This is the horizon problem, also sometimes called the homogeneity problem. The universe's geometry, which seems to be flat, particularly in light of new WMAP data, is the subject of the flatness problem. Even 14 billion years after the universe formed, when tiny variations should have grown drastically, the cosmos matter density and expansion rate seem to be almost perfectly balanced. Physicists need an explanation for why the small deviations haven't increased dramatically, as this hasn't happened. Did the variations not exist? Did they not grow into large-scale variations? Did something happen to smooth them out? The flatness problem aims to explain this. Why the geometry of the universe appears to be so flawlessly flat. These three types of universes are simplified representations of the way space naturally curves in the universe. First is the closed universe, where the universe contains enough matter for gravity to eventually overcome the space expansion. Such a universe has positive curvature as its geometry. This fit the original Einstein model, which did not include a cosmological constant. Second is the open universe, where the cosmos will always expand at the same rate since there is insufficient matter to halt it. This spacetime is saddle-shaped with a negative curvature. The third one is the flat universe, where the universe's expansion slows down over time but never quite stops because the density of matter and the universe's expansion exactly balance each other out. This space has no overall curvature. In 1980, astrophysicist Alan Guth proposed the inflation theory to solve the horizon and flatness problems. In this model, the early universal expansion accelerated at a rate much faster than we see today. According to the theory of inflation, any detectable large-scale curvature of the cosmos would have been eliminated by the ultra-fast inflation. It can be compared to growing a tiny globe to the size of the Earth. The local section you would seem to be very flat, but the globe is still curved. The visible portion of the cosmos appears to be almost flat due to the massive inflation of the tiny universe, resolving the issue of flatness. The reason the horizon problem is resolved is that during inflation, space expanded so quickly that these close regions were spread out to cover all of the visible universe. However, these close regions were then dispersed throughout the visible universe. The balloon's inflation can be used as a basic model to explain how the universe is expanding. Every point on the balloon is growing farther away from the center, thus a person at any point could feel like they are at the center of the expansion. The spaces between objects on the balloon's surface increase as it expands. The universe expanded by an enormous factor during inflation. This number consists of 26 zeros after the 1. It goes beyond the normal political and economic debate about inflation. Assume for the moment that someone wrote a message so small that it is unreadable on the balloon's surface before inflation. You will be able to read the message after you inflate the balloon. This implies that the writing on the original balloon is magnified by inflation, so it works like a microscope. We can also see quantum fluctuations that were generated at the beginning of inflation in this way. A massive microscope that magnifies quantum fluctuations to cosmological distances is created by the universe's expansion during the inflationary epoch. This leaves traces in the distribution of galaxies and in the hotter and colder parts of the cosmic microwave background radiation. Now that inflation is firmly established in our understanding of the early stages of the universe, cosmologists have spent the 40 years since Alan Goose's revelation figuring out the mechanism by which a universe can so suddenly and so drastically blow up. The dramatic phase coincides with the cooling and energy decrease that marked the end of the grand unification of fundamental forces and the rise of the strong nuclear force. It is theorized by some scientists that the decay of the X boson messenger particles that carried the electroweak strong force created a strong inflation field carried by a new messenger called the inflaton. This overwhelming new inflation energy drove universal exponential expansion, which saw quantum-scale irregularities instantaneously scaled up to large-scale structure. Transient quantum fluctuations became huge regions of overdensity and energy that eventually gave rise to galaxy clusters and superclusters in the present cosmos. The cosmos ultimately cooled and emptied as a result of all of this expansion, which caused the average energy levels to drop 100,000 times. The exact reason why inflation stopped is still unknown to scientists, but when it occurred, the inflaton field and particles decayed, releasing radiation and elementary particles into the universe, returning a large portion of that energy to the universe during a process known as reheating. This is similar to water vapor in the atmosphere condensing into water droplets forming a cloud. The formation of photons, gluons, and quarks, the fundamental particles, occurred during reheating but in a dense plasma state. Quarks and antiquarks started destroying one another. However, the mutual destruction of quarks and antiquarks resulted in an excess of quarks for some reasons that are still unknown. This difference, or an excess of quarks matter, is the reason that all galaxies, stars, planets, and people are here. Today, additionally, the grand unified theory states that during this period, the three extra fundamental forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, formed and then separated. The universe as we now know it had evolved. The four forces of nature and the rules of physics came into play. The universe was still too hot for quarks to join together to create protons and neutrons despite the fact that the fundamental particles had mass. Reheating ended at about a fraction of a second. Because of this, matter could be created completely and in a more expansive universe. The laws of nature were getting closer to being something we can truly understand and model. We are now entering the universe's third era, the duration of the electroweak era. The electroweak era lasted from an incredibly short duration. It is now starting to make sense as we move through the eras how a little singularity could expand so quickly into the present universe. The electroweak epoch marks the beginning of the modern universe as we know it because, by its end, all four fundamental forces would be distinct from one another. Additionally, we will see the creation of the first particles that would eventually give rise to matter. Most of us are familiar with the electron, proton, and neutron when we think of particles. However, did you know that there are many other particles and combinations of particles in existence? What exactly are these particles? Let's dive a little deeper. Everyone drives a car, uses a laptop, and has a phone, but have you ever wondered about the history of these materials? Matter exists all around us in four different phases: solid, liquid, gas, and plasma. The second form of matter is field, where four different forms of fields are observed. The electromagnetic field and gravitational field are well known due to events in our environment. The other two, known as nuclear fields, take place in the world of atoms. There are two types of nuclear fields, weak and strong, which have different field intensities. The corpuscular form of matter consists of two groups of fundamental particles. Fundamental particles, also called elementary particles, are the smallest building blocks of the universe. The key characteristic of fundamental particles is that they have no internal structure, meaning that researchers think about them as zero-dimensional points that take up no space. There are millions of different complex molecules in just one cell. When we magnify a single one of these molecules, we can finally see individual atoms. To put it simply, there are about 40 trillion cells in the human body, and each cell has about 100 trillion atoms in it. Atoms, however, are not the end of the story. If we could magnify more, at the atom's outer edge, clouds of electrons would be visible, and we will see empty spaces. If we magnify once more, but let's not stop there. If we could continue to enlarge, the nucleus would be visible at the center of the atom. However, the story does not finish with the nucleus. More magnification of the nucleus will reveal protons and neutrons sticking to one another. These particles are subatomic. Now, let's zoom in once more on one of the protons. We detect tiny dancing particles inside the proton. These are quarks. We refer to these little particles as fundamental or elementary particles. In the standard model of particle physics, there are 4 force carriers and 12 matter particles, in addition to quarks, which are elementary particles. So what classifies something as an elementary particle? If we look at the proton, it consists of 3 quarks. Therefore, protons are subatomic particles rather than elementary particles. Elementary particles cannot be divided into smaller parts because they lack substructures. This implies that they are made up of nothing. These are our universe's last and tiniest known building blocks. All matter is composed of particles called fermions and force-carrying particles called bosons. Leptons and quarks are the 2 types of fermions. Since leptons don't form groups and function alone, they are classified as solitary particles and are also fermions. They lack an internal structure, much like all fundamental particles. There are 6 different types of leptons: electron, electron neutrino, muon, muon neutrino, tau, and tau neutrino. When the 6 are arranged according to mass, the tau and tau neutrino are the heaviest of the group, while the electron and electron neutrino have the lowest mass. An integer charge, which is a negative or neutral charge, is carried by leptons. Their charge is a whole number or integer. The charges of the tau, muon, and electron are all -1. Additionally, the neutrinos are chargeless. Not to be outdone by leptons, quarks, which are the other type of fermion, are grouped together and also come in 6 different varieties with some of the craziest names found in particle physics. The 6 types of quarks are up, down, charm, strange, top, and bottom. Additionally, quarks are also arranged from weakest to heaviest in terms of mass. Out of the group, the bottom quark is the heaviest while the up quark is the lightest in mass. Antiparticles are oppositely charged particles found in all quarks and leptons. Leptons are solitary particles. As we have already discussed, they like to be by themselves. On the other hand, quarks only exist in groups and are highly sociable, so they combine to form composite particles. Composite particles are not regarded as fundamental particles since they are a combination of other particles. Composite particles are particles that are made up of more than one quark and, like other particles in physics, they have a name. These are called hadrons and come in 2 different classes. First is baryons, which are hadrons made up of 3 quarks, and second is mesons, which are hadrons composed of 2 quarks, 1 quark and 1 antiquark. Bosons are the fundamental particles that carry force, as we have discussed previously. For fermions, they act as glue. Bosons also come in 4 main varieties: graviton, governed by the force of gravity; photon, governed by the electromagnetic force; gluon, governed by the strong nuclear force; and W+, W-, and Z, governed by the weak nuclear force. Light particles, or photons, are massless. As a result, they may travel through a vacuum at the speed of light. But if all elementary particles were massless, our universe would be very different. A proton would not be able to trap a massless electron to create a hydrogen atom. Furthermore, the absence of hydrogen atoms means the absence of stars, galaxies, and life as we know it. All elementary particles were massless in the first tiny fraction of a second. However, something happened very quickly following the grand unification era, enabling some particles to gain mass. But how did these particles get mass? To clarify this, several physicists put up a theory in the 1960s. They suggested that soon after the Big Bang, a force field was created. When particles interact with this field, they gain mass. Today, we call this force the Higgs field. The universe is filled with this field. Through their contact with this field, particles like the W and Z bosons gain mass. The stronger their interaction, the heavier the particle. The difference between the massless photon and the massive W and Z bosons, as observed in nature today, can be explained by the existence of the Higgs field. Other force-carrying particles, like photons and gluons, remain massless because they do not interact with the Higgs field. There are two ways to identify a field. The electromagnetic field can be detected by observing particles interacting with it, and another option is to create the photon, a quantum particle connected to a magnetic field. But you cannot manipulate the omnipresent Higgs field. In order to see it, we must create the Higgs boson, a quantum particle that would be present in the Standard Model along with the other 16 particles and be crucial in explaining the interactions and behaviors of matter throughout the universe. By creating the Higgs boson through high-energy particle collisions using accelerators like the Large Hadron Collider, the Higgs boson decays instantly and is incredibly unstable. Therefore, it wasn't easy to detect or observe it. It instantly changes into particles that are lighter. For example, it might change into a pair of photons or 4 electrons. Scientists search for particles left behind by the Higgs boson by observing the collision debris. To better understand the idea, we can use the analogy of water and swimmers. The water in our example represents the Higgs field. A fish, being supremely streamlined, interacts only slightly with the field and can move through it very easily. In that case, the fish would resemble a low-mass particle. A man weighing 80 kilograms, on the other hand, could only go very slowly through the water. That man in our example is a huge particle that became massive through extensive interactions with the water. The electron is the lightest of the known subatomic particles, and the top quark is the king of mass in the subatomic world. It weighs almost 350,000 times more than an electron, or the equivalent of an entire gold atom. It is important to emphasize that we do not think that the top quark's larger size makes it heavier. No, it's not. Actually, scientists think that the electron and top quark are precisely the same size. Yes, they are both exactly the same size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. The truth is that none of these particles would have any mass at all if the Higgs field didn't exist. Currently, the Higgs boson is more frequently mentioned in the press than the Higgs field. How do these two items relate to one another? The smallest component of the Higgs field is the Higgs boson. We should go back to water once more to understand how that works. Everyone is familiar with what water is. As you can see, there is water all around you if you are submerged in it. There are no gaps in water. It is also known that molecules, notably H2O, make up water. You can now start to understand the Higgs boson if you combine these two concepts with the knowledge that water is made up of many separate molecules. Particles and subatomic particles are built up of an infinite number of distinct Higgs fields. Higgs bosons are composed of individual molecules exactly like water. Peter Higgs and François Englert won the 2013 Nobel Prize in Physics for their theoretical discovery of the same mechanism associated with the Higgs field. The theoretical framework explaining how particles get their mass was established by them. The particle has earned its place in the Standard Model, and the field its role in the evolution of the early universe. Remember, bosons are not the physical elementary particles, they are force carriers. This is a massive step towards physical matter becoming present in the universe, as the Higgs field can slow down other particles and impart mass on them. Another very odd concept to fathom is that this field is what allows our universe to support mass. Towards the end of this era, the weak nuclear force and electromagnetic force finally separate. Now that the universe has cooled down enough to allow all four forces to act independently, the laws of nature that we account for in classical physics begin to take shape. The quark era at this time, the universe cooled to about 10 quadrillion degrees, leading to a higher degree of stability. This marks the beginning of the quark era, defined by the interactions of matter. During this era, quarks and antiquarks rapidly form, collide, and annihilate each other. Antimatter, a unique type of matter, annihilates normal matter upon contact, releasing immense energy. For example, a gram of antimatter interacting with a gram of matter would release energy equivalent to the 1945 atomic bomb that devastated Hiroshima. Energy can create matter and antimatter in equal quantities. Since the discovery of antimatter in 1931, its existence has been widely accepted by physicists. A process called baryogenesis led to a slight excess of quarks over antiquarks, resulting in the matter we observe today. This imbalance prevented the indefinite annihilation of particles and antimatter. The reason for this minor imbalance remains unclear. Some theories suggest the universe slightly favors certain subatomic particles, like quarks, over their antimatter counterparts. This was observed in the 1960s. However, this difference alone is insufficient to explain the existence of the universe. Neutrinos, very low-mass particles produced in radioactive decay, with the Sun being a major producer, might hold the answer. Researchers are building particle accelerators and detectors to study the behavior of neutrinos and their antimatter counterparts. If their behaviors differ, it could explain the universe's formation through a process called leptogenesis, which involves low-mass particles. The buildup of quarks in the presence of gluons, a boson force carrier particle, created a densely populated quark-gluon soup. As the quark era ended, a new era began. The hadron era began and lasted from around 10 microseconds to 1 second after the Big Bang. During this period, the universe's temperature reached approximately 1 trillion degrees, allowing quarks to combine and form hadrons. There are two classes of hadrons, baryons and mesons. A slight matter-antimatter asymmetry from the earlier phase, known as baryon asymmetry, resulted in the elimination of most antibaryons by the end of this epoch. Only light, stable baryons, protons and neutrons, remained. Due to the high density of leptons, protons and neutrons rapidly converted into one another under the action of the weak force. However, as the universe cooled, these conversions slowed down drastically, leaving approximately 7 protons for every neutron. Since helium requires 2 protons and 2 neutrons to form a nucleus, while hydrogen needs only 1 proton, the excess of protons over neutrons led to an equivalent excess of hydrogen over helium, as observed today. To explain the apparent overabundance of helium in the universe, George Gamow proposed that most of the helium present today was created during the early stages of the Big Bang, in less time than it takes to cook a chicken. Gamow theorized that the cosmos began as a hot soup of particles, which he called delem, from the Greek word for the formless substance from which elements formed. He assigned Ralph Alpher, a PhD candidate, to figure out the processes that produced heavier elements from elem. Gamow and Alpher developed these ideas into a paper titled The Origin of the Chemical Elements, which established the standard for prestellar fusion and remains the basis for our understanding of how the high temperatures at the beginning of the universe transformed hydrogen into helium via deuterium intermediates. Protium, composed of a single proton, is the lightest form of hydrogen. These hydrogen nuclei existed as soon as quarks bound into protons. It's crucial to remember that neutral hydrogen atoms, which have both protons and electrons, would not form for some time. The sphere of space that would become the observable universe was approximately 10 light-years in radius. Era of nucleosynthesis around 10 seconds after the Big Bang, the universe had cooled enough for some deuterium nuclei, composed of 1 proton and 1 neutron, to form. Unfortunately, these deuterium nuclei remained unstable in the heated cosmic soup because of the high temperature and particle energy. If struck by a photon, as was inevitable under such densities, these first composite nuclei would break apart again. Physicists refer to this as the deuterium bottleneck, and until it was overcome, nucleosynthesis simply couldn't progress beyond the fusion of one proton and one neutron. It took about 300 more seconds for temperatures to drop enough for deuterium to become more stable and other elements to start developing. Initially, deuterium, with its one proton and one neutron, was able to fuse with individual protons under the intense compressive force of the universe, resulting in helium-3, a completely new stable element. Following this, the more common variety of helium, known as helium-4, composed of 2 protons and 2 neutrons, was formed. Helium-4 nuclei are the most stable atomic nuclei known to exist, and this stability, combined with the conditions of the early universe, caused the majority of unbound protons in the early cosmos to be absorbed into helium, preventing further decay. Even 13.8 billion years after this intense burst of helium formation, and the birth and death of innumerable stars, the universe still contains about 23% helium. This observation strongly supports Alpher's theory. If the proton-to-neutron ratio had been different, much of the universe's ordinary matter would have decayed into uncharged and unreactive neutrons and helium. Additionally, if the matter in the cosmos had been more compact during Big Bang nucleosynthesis, even more helium would have formed, leading to a universe made predominantly of helium with little to no chemistry, resulting in no galaxies, no stars, and no life. Fortunately, this was not the case. Even as many baryons settled into their stable helium nuclei, the universe was still full of latent energy, which could be used for further fusion. The race was now on to generate as many new elements as possible before the universe's ambient energy fell too low. After 20 minutes of universal existence, or around 1,200 seconds of intense cosmic nucleosynthesis, the nuclear furnace eventually slowed and died. It was too cold for any more nuclei to form, even if it was still scorching hot by human standards. At this point, there were just 4 elements in the universe: hydrogen, helium, lithium, and beryllium. Only the first 3 would survive long enough to witness the first stars and serve as the primary fuel for the creation of the other 98 naturally occurring elements in the present universe, due to the short-lived stability of beryllium nuclei. For now, there were 1 billion photons for each particle of composite matter and 12 hydrogen nuclei for every helium nucleus. With these basic ingredients, the stage was set for the formation of everything else. Even the deuterium and tritium that scientists fused together in California in 2012 were first formed in the heat of a newborn universe 13.8 billion years ago. After particles fused and broke apart to form nuclei, the primordial mixture of hydrogen, helium, and trace amounts of lithium and deuterium nuclei marked the end of the era of nucleosynthesis and led to the formation of the first stars. These were the universe's first nuclei to form. From being slightly bigger than a grapefruit during the grand unification era to having a radius of about 300 light-years today, the universe has grown in size due to ongoing expansion. As the universe cools down with its expansion, its temperature decreases. During this period, the temperature of the universe ranged from extremely hot to relatively cooler. Fusion stopped as the universe cooled to a certain point. We see how the nuclei will bind with other particles in subsequent epochs to form atoms, and later, galaxies. Era of nuclei. After the era of nucleosynthesis, we enter the era of nuclei. This period marks the end of nuclear fusion. The universe is getting bigger because it is expanding, though more slowly compared to the previous epoch. The universe's size has increased by a factor of 1,000. Now, the universe is a massive space filled with fully ionized particles. As the universe expands, it gets older and the pressure continuously decreases. Volume and pressure have an indirect relationship. As the volume of the universe increases, its pressure decreases. During this era, nuclei are no longer fusing together. The universe is still a ball of heated plasma containing completely charged particles. Nuclear fusion could not continue because the temperature became too low, but it remained high enough to keep all the atoms ionized and to prevent electrons from binding with the nuclei. For around 500,000 years, photons, the particles that produce light, were scattered in the universe along with electrons. However, they could not interact effectively because they were in equilibrium, preventing photons from escaping. The era of nuclei generated a lot of light, but it could not be seen due to the universe's extreme density. Photons would always collide with an electron or nucleus before continuing, making the universe opaque to light. The duration of the era of nuclei spans from 3 minutes to 500,000 years after the Big Bang. After 500,000 years, the cosmos cooled to 3000 Kelvin, at which point the nuclei of hydrogen and helium started to absorb free electrons. Since photons could no longer interact with electrons outside of very small energy ranges, the majority of the gas became transparent, allowing photons to finally escape the plasma and travel across the universe. These photons are what we now experience as the cosmic microwave background. When we look out into the universe, we can never see back in time beyond 500,000 years, which is the time of the last scattering of photons. Before this, all we could see was the universe's heated surface. We will now see what happens to the atomic nuclei, electrons, and photons as the universe continues to evolve. Era of atoms. We now proceed to the next era, the age of atoms, which began when photons separated from matter and nuclei started fusing with electrons. Once atoms formed, matter no longer affected photons or light particles. Thus, photons that currently form light and neutral atoms make up the universe. Space was literally made possible by the formation of atoms. During this era, the universe's temperature ranged from 3000 to 60 Kelvin. As matter and photons decoupled due to the decline in temperature, the universe became transparent. This means that when neutral atoms formed, electromagnetic radiation, including light, could travel throughout space with much more freedom than before, rendering the universe basically transparent to light. We can think of this process with the following example. Consider a parking lot filled with vehicles, our nuclei, and lots of people, free electrons, in between the cars. If you tried to make your way through such a packed mass of cars and people, you'd most likely be pushed back or deflected, scattered in all directions. However, if the people got inside the cars, the electrons joined with the nuclei to form atoms, there would be enough free space for you to pass through them all without getting deflected. This phase of the universe's evolution is called the recombination epoch because it saw the combination of nuclei and electrons to create stable atoms. The decoupling epoch got its name from the fact that light was ultimately able to separate from matter during this period. We see the cosmic microwave background, CMB, in low-energy light only because the expansion of the cosmos has redshifted the photon's energy to the red edge of the light spectrum. These photons originally had energy in the ultraviolet, a shorter band. Since then, the Cosmic Background Explorer, COBE, satellite has measured this background radiation and found it to precisely fit a perfect black body spectrum at a temperature of 2.73 Kelvin. This perfect black body radiation coming from everywhere is strong evidence that we understand the universe at least back to 500,000 years after the Big Bang. Nevertheless, the CMB shows us that the universe's structure and temperature were almost constant, fluctuating only by a few degrees compared to now. That was a very different environment. There were no galaxies, no stars, just this remarkably uniform temperature. Astronomers aptly term this era the Dark Ages. The universe kept expanding and cooling after recombination, marking the beginning of the universe's dark age. During this period, the Big Bang's brightness shifted into infrared wavelengths. This dark age, lasting hundreds of millions of years and beginning around 400,000 years after the Big Bang, was the last period in which the universe was truly empty. There were no planets, no suns, no galaxies, no life, just a fog of hydrogen atoms created during the Big Bang, left to float through the darkness. Today, telescopes around the world are trying to catch a glimpse of that primal hydrogen, known as neutral hydrogen, to pinpoint the moment when the Dark Ages finally ended and the first galaxies formed. Era of galaxies. In past epochs, we have witnessed the universe emerge from a tiny singularity to a massive universe full of atoms. Let's investigate the galaxy's era to learn how the universe reached its current state. Our universe continues to evolve within this timeline. The force of gravity caused matter to draw together to form galaxies. The formation of the first galaxies marks a major transition in the evolution of structure in the universe. These same galaxies changed the intergalactic medium from neutral to ionized, thanks to their second-generation population 2 stars, zero metallicity population 3 stars, and black hole-driven sources such as mini-quasars, X-ray binaries, etc. This process is known as the epoch of reionization. The formation of stars and quasars occurs during reionization. They start to release powerful radiation, which causes the neutral hydrogen atom to break apart into free protons and electrons. Reionization eventually comes to an end, and hydrogen atoms form again. It is thought that the energy from these initial stars, early galaxies, and incredibly bright quasars with black holes at the center helped reionize the hydrogen gas. In this case, ionization is the process by which the energy of the star extracts electrons from the atoms in the surrounding gas, causing it to glow. Since this is the second time the gas has been energized since the Big Bang, this age is known as reionization. As a result of the combined energy of these first stars and galaxies, light was able to travel farther into space than it had previously. Probably the most pressing question in astrophysics is finding out more about early star formation, which will help us comprehend how early galaxies or groups of stars were formed. The newly launched James Webb Space Telescope was created in large part to answer this question, as its infrared capabilities allow it to see highly redshifted objects like these early galaxies. After that, the galaxies are gradually drawn closer to one another by gravity, forming clusters and superclusters. A path for stars to develop and ignite was created by the difference in density in the cosmic microwave background, and these stars eventually gathered together to form galaxies. The universe is expanding with a diameter of 93 billion light-years at this period. Moreover, the temperature of the universe is between 60 and 2.73 Kelvin during this epoch, which spans 1 billion years from the Big Bang to the present. As new galaxies form, the universe is still evolving. Indeed, we are living in the era of galaxies at this very moment. Matter distribution in the universe, dark matter and dark energy. Dark matter appears to be widely distributed around visible stars in galaxies. Galaxies collide with one another because the dark matter halos make them appear larger than they actually are. The collision of small galaxies results in the merging and formation of giant galaxies. The two basic components of the entire universe are matter and energy. The majority of the matter in the universe is invisible, and most of the energy's source is unknown, which presents a significant challenge to scientists. If much of the universe is invisible to us, how can we study it? Scientists will remain at the forefront of the search for dark energy and dark matter as our observational techniques become more sophisticated. The distribution of dark matter in merging galaxy clusters, such as the Bullet Cluster, is mapped with the help of NASA's Chandra X-ray Observatory and optical telescopes. X-ray observations reveal a heated shock front where the cluster's gas clashed and slowed down, but measurements of gravitational lensing reveal that dark matter remains separate from regular matter and unaffected by the collision. A theory suggests that some dark matter particles undergo annihilation in a burst of intense radiation, making them disappear. Dark matter annihilation signs have been identified by the Very Energetic Radiation Imaging Telescope Array System in Arizona, which is equipped with gamma-ray detection capabilities. Researchers are examining how dark energy and gravity have clashed throughout the universe's history by comparing observations of galaxy clusters with experimental models. Thanks to modern methods, we can calculate the quantity of dark matter present in a galaxy by measuring the bending of light from background sources. We can estimate the mass of a galaxy by measuring the degree of that bend using this gravitational lensing technique. When the mass we calculate from the bend and the mass we can observe directly don't agree, we know dark matter must be present. We know that dark matter exists even if we cannot see it. About 4.5 billion years ago, our solar system formed from a dense cloud of interstellar gas and dust. The cloud collapsed, possibly due to the shock wave of a nearby exploding star called a supernova. When this dust cloud collapsed, it formed a solar nebula, a spinning, swirling disk of material. The planets formed in a thin disk circling the Sun, which formed at its center. Moons evolved around the gas giant planets in a similar way. Similar to every other planet in our solar system, they originated from a disk of gas and dust circling the young Sun. The forces of drag pulled the dust particles together to form rock clumps that eventually evolved into what scientists refer to as planetesimals, which are tens to hundreds of miles across. After these protoplanets collided with one another, Earth, our home planet, was created. In the universe today, matter dominates over radiation. Protons, neutrons, and electrons, the known building components of atoms, as well as the mysterious dark matter, make up matter. Most of the radiation in the universe is in the form of the cosmic microwave background. Remarkably, despite its extreme weakness, the microwave background radiation still has more energy than all of the known stars and galaxies combined. This is because, although being extremely powerful radiation emitters, stars and galaxies only make up a very small portion of space. Physically speaking, our universe appears uncannily perfect. If it were any different, life as we know it, planets, atoms, and everything else wouldn't exist. Our universe, in all its grandeur, is a finely tuned symphony of physical laws, fundamental constants, and cosmic forces. This is not just a random collection of matter and energy, it is a masterpiece of precision. As we continue to explore the cosmos, we marvel at its elegance and wonder. Perhaps the delicate balance that sustains our existence holds secrets yet to be unveiled, a cosmic ode waiting for us to decipher its notes.